Join me in welcoming our speaker today, Michael Wood-Vasey, who's going to be talking about supernovae survey software and statistics. Michael is in town visiting LSST and Sphere Observatory for the latter part of this week. He has had a long history in surveys, and especially in time domain surveys. He started as a graduate student at Berkeley. I think he's been supervised by two relatively obscure people who have really good parking spots on campus, Saul Perlmutter and George Smoot. He has worked on the Essence survey at Harvard. After that, working on image differencing and on making that survey useful for science or utilizing it for science. He's also worked on PenStars. Afterwards, these days, he's a spokesperson for the SDSS, the RE collaboration. And today he's here. He's going to tell us something about all his experiences in getting science and getting data out of big surveys. So thank you.
Thank you, Mario. It's always a pleasure to visit here in Tucson. Since I'm in the NOAO conference room, particularly NOAO, always a pleasure. Speak of the Essence and the now postdoc show up here. Welcome, Gotham. I've been involved in surveys for a long time, and one of them, just to make sure we're hitting all the important notes, Essence was an NOAO survey. We'll be getting the final data to you any day now. But actually, all the processed images have been released. But just a little supernova, just to build a little bit here, right? We've always been interested in exploding stars, and to start with the most naive detector, which most of you have two of, some with augmentation, we can see supernova in our own galaxy. So supernova 1006 was seen, and a handful of others have been seen over the past millennium. Ones were almost certainly seen before that, but it's important to write things down and to preserve those libraries from getting destroyed or burned or things like that. So documentation is key. That's our first software-related note. But 1006 was widely seen, and through federal funding at the time, supporting the Chinese astronomers making maps was indicated here on the survey. Data access was very difficult. You had to go in person. You had to ask nicely. There were no remote copies of this. We still see 1006 today, right? It looks like this. It's a supernova remnant. The supernova remnant and the supernova communities are different, perhaps because we're just impatient. But they are both important expressions of the end of life of stars that we see in our own galaxy. We've gotten better. We've gotten better through improved detectors and improved searching. So the first improvements were really technological detectors, from eye to photographic plates to CCD, and then how you could do the computing on those ever-growing CCDs. So CCDs continue to improve, and they're certainly much, much more civilized and nicer today in 2014 than they were in 1994. But it's really been the ability to first be able to run on significant clusters, now to put a whole bunch of CCDs together to recover the fields of view we used to have on these survey telescopes. And in the future, hundreds of thousands of surveys from things like supernova, from surveys such as LSST, will be enabled by being not just having computing resources, but by being intelligent about it. So this actually stands for advanced intelligence, not necessarily artificial, but injecting intelligence into what's searching. So I'm going to just touch upon several current surveys. I'm not going to talk about the one in the upper left, which is the dark energy survey. But that's one of the big current efforts, speaking of survey projects with NOAO resources happening. And there are a variety of others. SkyMapper, SDSS-2 was a use of the SDSS telescope to use supernova in the previous incarnation, and even more local things like CATE and PTF, the Catalina Sky Survey, efforts such as that. I'm going to first talk about something I had nothing to do with, just to clarify. This is the Supernova Legacy Survey and the latest Type 1a Supernova Hubble diagram from them. I'm assuming at some point in your lives you've all seen a Type 1a Supernova Cosmology talk. Has anyone not seen such a talk? Okay, just thought you didn't want to necessarily see another one, but this is relevant. So this is a combination of 4 different surveys from the low redshift to SDSS to SNLS, and then a few from HST, although there are more from HST coming. And this is plotting our distance modulus versus redshift. And of course, if you plot this versus log z, this is almost, but not quite, a straight line. And I think this illustrates several different points here. One, this is a combination of surveys, each optimized for a different redshift range. Two, this paper is the analysis paper, but really it's built, this is by Mark Patouille, led by his work in 2013 at doing the cross-calibration between these surveys. That was the key thing that allowed that, the cross-correlation between Supernova Legacy Survey and SDSS. He was not able to do quite as much with the low Z because they come from such a diversity of sources. But this is how we are. There are about 740 supernova, what people consider the gold standard of what you would do supernova cosmology on right now. Just to remind ourselves, since supernova were originally used, type 1a supernova distances to very explicitly demonstrate a dynamic dark energy, dark energy affecting the dynamics of the universe. This acceleration is the fact that we do not live in a omega lambda 0 universe is at least 4 or 5 sigma to some point where no one believes that your tails are Gaussian. So we'll just call this 99% confidence level that there is something there. And that's because supernovae themselves do such a good job of figuring out the difference between omega matter and omega lambda, right? That's why this is the slope. Whereas things like Planck and WMAP tell you the sum of those things, loosely speaking, from the early universe. If you throw in baryonic acoustic oscillations, giving you a couple more distance measurements, we actually all tighten up really well right here. But it's the supernova, really, that are sort of eliminating a lot of the distance of what purely the evolution of over time. If you combine the supernova and the cosmic microwave background and baryonic acoustic oscillations, then you can start to learn about the nature of this dark energy. What is W? What is the relationship between the pressure and the density? And this is a compilation of supernova in blue, the Planck CMB constraints in green, and overlaid the combined results. If you add in the BAO, gives you a point here. That is consistent with our model, but no theory, of saying that there's some cosmological constant, which would have a W of -1. By continued improvements in each of these probes over the next decade, very much from large surveys such as LSST, but also other efforts, we're hoping to figure out the very, very simple question. Dark energy exists. Is it something other than just being W equals -1? Some people care about the amount of matter in the universe as well, and things like lensing surveys can tell you a lot about that. Just to give you a reminder of what we're talking about in terms of the scale of things, the difference in magnitude over redshift 0 to 1, because these are relative distance measurements, of a W of -1 versus -1.1 is about 0.04 magnitudes, 4 to 5%. So the existence of dark energy is a 10% measurement. Figuring out what it is a 1% measurement. And if I were an astronomer, I would have said, well, that's silly, that's really difficult, and gone done something else. But actually, I hang out with physicists who think that that's not even difficult. And so they blithely go on and try to do that in astronomy, and it turns out that calibration is really, really difficult. But that's what we're trying to do, just to give you a sense of what are the size of just measuring magnitudes that matter here. So the largest systematic, this is from Alex Conley's paper, 2011, is the calibration uncertainty. That's the largest systematic contribution in the W omega matter plane. And so it's critical that future surveys improve and work on this. LSST has made many statements in the right direction and plans in the right direction. Until the data flow, we'll never know. I think obviously the dark energy survey experience with this will be very informative. But to visually illustrate this, this is statistical only size area in this contour plane, and this is if you include the systematic uncertainties from the calibration. So that's why this is saying that 80% of that relative areal increase is from calibration. Okay, so I spent a little time with pan-stars. This is some other. Pan-stars surveyed 10 fields across the sky. This is the sky in a projection no one actually sees. We're seeing the galaxy in black, and we try to be mildly intelligent and not look through too much of the galaxy and just cover several fields in it. And thousands of type 1a supernova were found through this, and in Armin Rest and Dan Skolnick wrote a pair of papers, which Gotham was involved, certainly, doing the first cosmology results from that. Here's just an example, both from pan-stars and just to illustrate what it is that we do. We take a series of, in all these supernova searches, we're taking a succession of images, we're taking the difference, and we're measuring the light curves. And you can do that in Flux. You can be an astronomer and convert that to magnitudes. You can try to care something about astrophysics and look at the color evolution of what's happening. And from these data alone, we've actually done a decent, although not sufficiently perfect job determining the type of the explosion, making sure it is one of these standard 1As with a known brightness. Okay, but on to a bit of LSST. So that one of the reasons I showed this figure, this is where the supernova is coming from, is to contrast it or to set up this figure. LSST, instead of just doing several of these regions on the sky, these black ones for pan-stars, or STSS2, which did a significant swath here, it's going to do half of the visible sky. You can argue about exactly which cadence or whatever, but in concept, that's what it's doing. And that's why you get hundreds of thousands of supernovae. So that's both important for how to get all of those just in the numbers. It's actually just scientifically interesting. Does the universe really look the same there and there? We're just getting to the part of being able to explore that. Because the basic question of dark energy, does it vary in time? Does it vary in space? Does it vary in local gravitational potential? These are all keys, basic questions that we'd like to ask about it. So just for a sense, what you can do with 100,000 supernovae, you can do one of these Hubble diagrams. Remember I said we had 740 in the current sample. Let's round that to 1,000. You can do 1,000 and 100 different parts of the sky. So this is just a two-mass measurement, a two-mass illustration of the sky, which I picked not only for its foreshadowing, but also because you can actually see all these things across the whole sky. And we can just ask this question, is dark energy the same here as it is there? We don't have that many viable theories saying it should be different, but it's a very, very simple question that we should address. You could turn that around and say, if you're willing to assume that we should be isotropic, you can have a very good test of any systematics that you might have, particularly in your calibration. So some of the big challenges for future type 1A cosmology, we're trying to do this with photometric information alone. Things like pan-stars and DES are teaching us something about that. But we really have to figure out what's going on both in the color relationship that relates to questions about other dust, and then the calibration, which is so important it didn't even make it onto the slide, because it's sort of more of a survey level of thing. But also, is there something about different supernova? Are they really type 1A supernova all really the same thing, or are there hints of multiple populations contributing? And that would be a problem if those multiple populations contributed in different amounts over time. Right? It's not like an individual supernova knows what time it is. It doesn't measure the radiation temperature of the cosmic microwave background and decide to explode in a certain way. It has some history, embedded history of star formation, elements that formed it, some binary fraction distribution that it came from, or whatever, that would be any difference in the brightness. So I will argue, and I'm not alone, that really the right way to do this is to use the near infrared, which, as a hint, I've made difficult to read here because it's difficult for you to see it. So near infrared helps in a couple of different ways. It helps in the very simple thing of just determining dust. So here's some examples from Foley-Kelly et al. 2010 of taking two supernova, well, 4 supernovae here, and looking at their relative excess over wavelength. Right? So this is an inverse wavelength. And so we're going from the near infrared on the left to U-band on the right. So looking at this color excess, these two supernova have a color excess that seems very in accordance with the standard dust extinction law with an RV of 3.1. These two supernova seem much more consistent with having gone, their light being processed through dust, with an RV of 1 or maybe 2. If you just had the optical information, that wouldn't be enough. And actually, frankly, if you just had the near infrared, that wouldn't be enough. It's the combination that are allowing you to tell you that. And so I take this as saying we have to worry about both things. We have to worry both about general dust that looks sort of like the dust in our galaxy, and maybe we have to worry about very local dust to a supernova or environment that might change what's happening. Luckily for us, type 1A supernova are standard in their brightness in the near infrared, specifically in H band, so 1.6 microns. That's very helpful, both for the specific desire of just trying to measure distances, but also because of this dust question. If they're very variable in the near-infrared, it'd be very difficult to figure that out and make these color access demonstrations. But they are standard. There's some very key work a decade ago done by Kevin Christiunas. I followed that up a little in 2008 with some work on Paratel. It's the old 2-mass telescope on Johns Hopkins. There's been some more recent work by Baron Nugent using Gemini, which is why the error points are smaller, at least the statistical photometric, than these points here, and exploring out what is the residual brightness versus just a smooth expansion. So we're in the nearby Hubble flow. We're at cases where you can write down kilometers per second and not feel ridiculous. So this is 10,000 kilometers per second. Or in redshift, you want to think about this. We're exploring out sort of 0.05 to 0.1. It's a little further here. In which any of those different models of where we live in cosmology, they all make the same line. So you don't have to know the details of exactly what dark energy is to be able to use a simple relationship between redshift and distance and be able to check these things. So there are a number of different attempts and efforts doing this. The largest is the Carnegie Supernova project in the Southern Hemisphere using a combination of SWOPE, telescopes DuPont mainly, and then supplements by Magellan. There's some of the work on discussed. There's some work on HST using supernova from pan-stars and now DES. There's the Paratel work that was done. And so we recently, finally, put out a paper from this led by Andy Friedman that introduced 94 type 1a supernova into the literature, and we're just getting started analyzing those. Most of those are sort of in this redshift range, but that will really help to listen. And then I'm leading a 3-year, we're in year 3, just about to start, a survey on wind using the work detector infrared, which we've named Sweet Spot because we are in the sweet spot of wavelength, the H band, with the supernova standard and unaffected by dust, and the sweet spot in redshift where we don't have to know the cosmology, but we're not as bothered by the peculiar velocity. That's what these dashed lines here were. This is the uncertainty just from a typical few hundred kilometers per second peculiar velocity, or 150 kilometers per second. And so you need to sort of be away from this to really be able to make some good distance measurements. So sweet spot is goal to make an H-band Hubble diagram to a redshift of 0.08. I suppose verify, that's a leading question. Test that. Type 1a supernova really are standard candles in the near infrared. But test some other correlations. So I mentioned that calibration was the biggest systematic in optical type 1a supernova distances. But there seem to be some weird relationships that after correction, for things like color and the width luminosity relationship for type 1a supernova, there's a residual brightness of the supernova that correlates with host galaxy mass. It's just at a level to be enough that it would be significant, but small enough that we can't quite clearly tease it out. It's not clear if this is something really funny in the fitters, if this is something telling us about these different populations. So we wanted to test this in the near infrared. We want to generate a set that improves an understanding of colors across optical and near IR, both at early times and late times in the evolution, so you can do more tests looking at the dust. And if it turns out that these really are good standard candles to 10% in brightness, thus 5% or so in distance, and this will lay the anchor together, particularly with the Carnegie Supernova project, for future higher redshift work, which becomes difficult because the atmosphere is very difficult to look through and you might have to go to space, but nonetheless it'd be useful to have. I return to this point of the all-sky stuff. I think it's actually very important that we have both Sweet Spot working in the north and the Carnegie Supernova project in the south, because these are setting an anchor in the nearby universe. We're measuring distances to individual galaxies in the nearby universe, and we'll eventually be able to put together a flow model from the supernova alone. But calibration is really important, and calibration in the infrared is actually historically even harder because of water vapor, which is essentially Y like Z and Y, and then J, H, and K are defined. So the near infrared is just even worse, but I highlight this because this is a paper by Colin Blake and Margaret Shaw, illustrating that you can account for this variation in the water, which looks very complicated, but is all a coherent shift, by measuring the GPS delay. So geophysicists hadn't figured this out to get precise measurements of distance. And you can use the delay in the GPS signal from the integrated optical path, the extra delay from having water, right, which is a higher index of refraction, to tell you how much water is in that column. So this system is being used by DES and is scheduled for installation very soon now here at Kip Peak as part of this project. So our goal is to get one gross, 144, type 1a supernova. In some sense, you could take the square root of things and say this is sort of a 1% distance measurement at a redshift of 0.05. But in general, this is our prediction. So these are some simulations we ran. The gray dash was the literature at the time that I did this stuff. The Friedman stuff just came out recently and we populated a lot of things here. Blue is sort of a one simulation of what we might see. Red is the very early data that we just published earlier this year. And this is how maybe they would look, assuming that they are standard on a Hubble diagram. So this is sort of conceptually what we're going for here. But our first early results, we used 12 supernovae that were well separated from their host galaxy from a 2011 B pilot survey. This is before the formal NAO survey. These are in redshift order. They go out to redshift of 0.09. And here, you may not be surprised, with WIN, which is a fabulous telescope, and WIRP, which is a nice detector, if the scene is 0.5 arcseconds, we can go to a redshift of 0.09. If the scene is 1 arcsecond, we can go to a redshift of 0.06. And it just makes a huge difference. And I think certainly the operators and the staff and the engineers have all been very helpful in working with us. Particularly, a lot of work on WTTM has been key in allowing us to get some of these images, allowing us to reach out in redshift. Now, honestly, except for some sort of bragging rights, these were the furthest two published at the time. We don't really care about going to redshift of 0.09. Going out to 0.06 is all we really want to do. But volume is volume, and you often get more out there. So we threw out one of them because it was spectroscopically identified as being at least optically a non-standard 1A, a 91 BG-like. And from that, we constructed our Hubble diagram, in which the red points are here. And I'll mention that in 2011B, we were awarded 7 nights. The weather was almost as bad as it is right now, and we only got 3.5 usable nights. So some of these points, the ones in circles, are from one near-IR data point. So one of the things we want to figure out is what is the minimum number you need? Because if what you need to go to a redshift of 1, which may require cryogenic, maybe not, cooling in space, if you need 1 point or 20 points, it's a very, very different discussion of what you might be able to do. If you need 1 point, then maybe you can get enough JWST time together with LSST or something to hit some of these. If you need 20 points, this is just a non-starter, even more so than the first point was. So this was published earlier this year. Anya Wyant is the graduate student who led much of the observing in this paper. So still standard in H. So here is the new redshift distribution. Here is the spread, if you will, around the residual 0 for each survey. So for all, this is sort of the spread. And for each individual survey, this is a collection of things. This is the Carnegie Supernova Project 1. This is the stuff I did in 2008. Here are the Gemini ones. They do really look nice. I actually don't know why they didn't get renewed for time. We should have this conversation again. And this is the stuff from Wyant 2014. Remember, including some supernova with only had 1 point. So one of the things when you look at the residuals, you want to say, do they vary with respect to anything? So remember I mentioned before that the optical brightness of type 1a supernova, after correction for the known width luminosity and color luminosity effects, has this correlation. So this is what it looks like. So this is from Mark Sullivan, 2010. There's also been work by Pat Kelly and Lumpedal about this. It's been seen in different ways in some different surveys. So you have all these points. And if you bin them, and you ask where is the split, you can find that at a log host galaxy stellar mass of 10 to the 10 solar masses, there seems to be a jump in the after correction brightness of the type 1a supernova. That could be at the scale of 0.1, 0.08 magnitudes, which seems huge, right? Except that you're getting all these things mixed in. You're getting some of these at every redshift. So is this two populations? Is this something funny that we haven't really understood about something we understand about a calibration set for training light curve fitters? Which remains a possibility, but I don't think anyone really thinks that's the answer. Or is this something telling us about different populations of supernova that might change how many you have of each over redshift in a very subtle way? And that could mimic this, 1, 2, 3% variation now that we're looking for to try to measure things about dark energy and W. So this is the histogram version of this, right? So this is all of the ones higher mass than this project out into the gray region and have a mean at this dotted line. All the lower ones project out into this dashed line and have this dashed mean. But it's not clearly staring you in the face that these are separate. You could be cynical and say, well, if I take any set of data and ask where's the jump, I might find a jump. This is more than that, but this has really been sort of nagging at us, trying to figure this out. In particular, one of the things you might want to say is, well, if this is really true, I do separate Hubble diagrams or separate analyses just based on a difference in stellar mass. And if I do that, is it really a jump discontinuity? Is there some fit? Is there some smooth thing? I don't know. So let's learn more about these. In particular, is this also seen in the near infrared? And this host relation was a distant second, but the second biggest systematic identified in the Conley 2011 paper.
Is the chi-square of null of constant?
I don't, well, I literally don't know the answer to that question, but the problem is that it is not well defined in the analysis. So what we find is in type 1a supernova, when we correct for the width luminosity and color luminosity relations, that there is a remaining, what we call intrinsic dispersion of on the order of 0.15 magnitudes. By which we mean, if we add 0.15 in quadrature, we recover a chi-square of 1. Now, there are formal ways to do this fitting a little better and use it as a fit parameter. But if we have constructed that intrinsic scatter based on the observed dispersion, we can always get that chi-square by looking at that. So one of the themes we wanted to that I'm exploring a bit is to what degree would two populations blur that out? If you took a one population model when you actually have two, what would that difference be? Okay, so we did this plot. This is for the Wyant 2014 analysis, where we've taken the different data sets for which we could get good host galaxy information, which to be simplistic means was it in the SDSS footprint, because that's just the easiest thing to do. Because you want to make sure that you're all on the same scale. I don't want to spend a lot of time trying to figure out how B and V map to G and R for estimates of stellar, right? I just want something that gives me all the data in a nice, simple way. And then I've symbol coded each survey. So the Wyant 14 points are circles. The Wood-Vasey 08 points are upward triangles. The downward are triangles with CSP. Brown-Nugent are squares. But then so this is stellar mass. And you can spend a lot of time and try to see, do I see the same discontinuity I saw before? But it's not clear at all that you even have enough numbers to see this. So that's one of the reasons we need these numbers. And this was just from sort of the 50 supernova we could get the host galaxy information for as well. This is, again, just based on the pilot data. I've also color-coded by the color of the galaxy. Okay, and the very, very sophisticated convention that blue galaxies are circled in blue. And red host galaxies are squared in red. Now this, of course, is related to stellar mass, right? Because these older galaxies with more stars, are red, and the small dinky ones still making stars are blue. But that's setting that up. Okay, so I'm keeping this convention throughout here. Let's return to our Hubble diagram and try to figure out where these are. And you'll start to see one particular thing if you look at the blue. It doesn't seem to vary quite as much as the red. And you saw that here too, right? The dispersion in the blue points is less than the dispersion of the red points. But unfortunately, that's also true of the photometric uncertainties, right? Because the normalized dispersion might be sort of much more comparable. And so we can look at this with respect to, so this is the residual that plot. And by this point, maybe if you're really good at counting circles versus squares, you might have noticed that actually almost all of the blue points come from the Baron-Nugent Gemini data. So unfortunately, the astrophysical blue versus red separation of the host galaxies is also very correlated with the different surveys and the different instruments and telescopes being used. And so suddenly, we started to write a paper, when we step back and say, wait, we need to understand more what's going on about this, because I don't want to say something astrophysical about that. But I'm giving a talk and not writing a paper, so I'll show this to you. But we started to look at these questions. Okay, but actually, I did stellar mass. And I have one that also does an estimated star formation rate or whatever. But actually, what's our observable color, right? Or magnitude, right? And these are all sort of local 0.05 redshifts, so we don't have to obsess about K corrections too much. They separate very cleanly and easily in color. You see the dispersion is less, and you can see more clearly that these are all blue squares. You can get clever, and you can ask the question, well, if I just look at absolute brightness, so this is, again, sort of related to the stellar mass, right? But it is the observable, almost. It's the apparent magnitude plus the distance modulus. Either sort of clear, and if you try to make this sort of diagram as the Sullivan paper did, right, showing some different subsamples, I don't know. We could say that they're different, and maybe there's a little bigger spread, but... So there's another interesting thing that was observed. So in a paper by the Supernova Factory, led by Rigaud et al., the paper, they have an integral field spectrograph. So they take a spectrum of the supernova and the galaxy around it in multiple different points. I think it's 15 by 15. And what they found is they found a correlation between the residual brightness of a type 1a supernova and the local H-alpha formation. Not the global galaxy one, but the local H-alpha formations. So indication of recent star formation. And they made a similar split. They found that there might be a significant split between these two different modes. Perhaps up to 0.2 magnitudes, but even if we're conservative or whatever, 0.1 magnitudes on this order. Now, how does this relate with the previous question? I know we're switching optical to near infrared, but about the color of the galaxy. Right? So this color is a very global measurement. The H-alpha is looking specifically. And I mention this not because we have this information for all our galaxies, although we're working on that, but because all of these talk about whether or not we have sort of two populations or whether or not we have correlations between the supernova properties and the host galaxy properties. Those are the key questions. And so this is sort of breaking out what the Rigaud paper was looking at. So this is their residual Hubble diagram. This is the stellar mass. Here's that 10 to the 10 mass split point that I was showing from the Sullivan paper. And here's how they project out the residual, the number in each of these things. So if we project out the residuals and we split them in terms of the supernova associated with recent star formation versus those without recent star formation, without locally where the supernova is, then the ones with recent star formation with supernova seem to be nicely behaved. Or there seem to be, perhaps you could argue, two populations of the other. So you could break this out into two populations. You can make up various stories about what this says for the progenitor, things that are difficult to test until we see an actual progenitor. But I just want to reemphasize another direction in which to think about, just maybe empirically, phenomenologically, we have two populations. From some form. I'm not making a statement about progenitors or whatever. I'm just saying observed. There are various ways of splitting. Does that split change with redshift? Because that is sort of what we would be very afraid of. So returning, I think, to the earlier question, well, what would that look like? Well, just as sort of an exercise, here are two Gaussians added together. This took probably half an hour. This is magnitude, this is a small shift. Can you tell that that's not Gaussian? And more to the point, if I subsample that with only 20 samples, how well can you tell that? you tell the difference between this Gaussian and that Gaussian if the way I was determining the spread in the first place was matching chi-square to 1, or saying that there's some 0.15 magnitude spread? It's not particularly obvious visually. And this was an extreme, well, this is a significant shift. This is a shift of 0.15 or 0.1 magnitudes. This is a shift sort of at the level we're talking about. So have this whole time, now we've been saying populations have a dispersion of 0.15 magnitudes, and actually we have two populations with smaller dispersions. If you care, the formal thing that you would get is the quadrature sum of these two sigmas plus the relative weights plus the times the magnitude difference between them is what you would assume the simple one Gaussian model would be. So you're not improving this, but if you can identify this, you can improve on that. And even more to the point, if you conclude in your model some allowance, there might be some shift in redshift, maybe you can account for this in a way that maybe you can't with 20. But if you have 100,000 supernovae, then maybe you can see this behavior much more clearly. And so here's very simple. Well, here's the model. So my graduate student, Kara Ponder, has been working on this. And this is a 1 magnitude split for visual clarity. We are not in this regime. But it'll make all of these plots visible, right? The whole point of this was this is sort of hard to see. So this is a simulated sample drawn from a 2-population model. Here's the fit, if you're incredibly naive with your 1 Gaussian thing, which has 2 parameters, right? Mean and sigma. And then the 2-population model has 5 parameters, 2 for each Gaussian, and 1 talking about the split in between them, or the relative weights. And so here's one way to visualize how this might happen. Let's say that these populations evolve with redshift. There's more population A at redshift 1 and less at 0, less of population B at redshift 1 and more of it at redshift 0. So here we're showing the histogram. This is a stacked histogram in redshift. So let's spend a moment. So there's a color coding in redshift going from red to blue as you increase in redshift. Sorry. Okay, yeah. It looked pretty. Should have thought that one through better. So at low redshift, you're sort of drawing more from this population. Right? As you go up to higher redshift, you're drawing from the other population. This is stacked. All the redshift bins are being added together. So if you looked at the entire sample with respect to the correct cosmology, this is presumably what you would see. But again, we've magnified the effect by a factor of 10. If you shrunk this together, I don't think you would see that very clearly at all. But if this is part of your model, you can now account for that. And with the increased number of data points from the ever larger surveys, maybe you can fit for that. So here's an illustration of what goes wrong. So with this ridiculous 1 magnitude split, the blue, again, is the single naive 1 Gaussian model in populations. The red is what those populations actually look like. So we've shifted from population B to population A as we go from 0 to 1. I'm calling this B and that A. Your nomenclature may differ. Okay? So B and A. The blue is the mistake you've made in the estimated mean from doing this. But if you actually you knew the evolving model correctly, you could get that exactly right. This wouldn't bias you if you knew what that model worked. And I will argue that with the large samples of things you get from LSST, you can fit for this. How do increased statistics allow you to do systematics better? They allow you to either select out subsamples or more sophisticatedly fit for those distributions. And you can do this separate from cosmology. You can say, I don't care at all that these are standard candles. I'm just going to take all the supernova to redshift from 0.495 to 0.505 and look what their distribution is, respect to their own mean. And I'm going to do the same thing at a different redshift bin. And I'll say, do these have a different skewness, right? Or are these both sort of a similar mixture? You can do all these tests separate from all of this. So Kara is working on the analysis framework to do this. So formally, we're generalizing the question of likelihood. Right? So that's what you fit here. You're basically saying that our model uncertainty is not some simple 0.15 sigma intrinsic dispersion. It is this. This is the likelihood function that you should check. So that's what she's implementing in her code. And so this would generalize to any systematic that you wanted to do, but we're starting with something very specifically and recently motivated by data. Okay, so let's return to our near-infrared residuals versus host galaxy properties. So host galaxy color is on the left. Absolute magnitude of the galaxy is on the bottom. If you know something about astronomy, you will not be shocked to see this behavior. But I'm just showing sort of where our supernovae have been drawn from. And this color coding is the residual. So these were a little brighter. Excuse me, red were a little fainter. And except for, you have a couple of these blue points here, the variety of colors is less here. The variety of colors is greater here. And that's equivalent to this having larger residual spread and this having smaller. Right? We're just compressing axis into color. So again, one of the problems was most of all of these are from one survey, and we want to change that. And so here I've color-coded in by the survey. So again, all the square boxes are from the Brown-Nugent. We just have a couple of other ones here. This is from the early pilot data, 2011B. We now have data from the first 2 years of our survey. We're analyzing the first half of it, the first 3 semesters, 2012B, 2013A, 2013B. Sorry, you could have done that. To add to this, and so I've had a fabulous high school student who is now on his way to Caltech, or has already started at Caltech, who on his own taught himself how to use NED, how to use SDSS, how to use Blanton's K-correct and IDL, by the way, and he gathered all this data and made these plots. And so he's gathered all this data for all the host galaxies that we can get this for from those first 3 semesters, and he got ahead of us being able to actually calculate the distances to them. So there's going to be no big reveal at the end. I don't have distances to 100 supernovae new from our data release, but I do know where they will fall in this diagram, which was the point. Our earlier big concern was the Gemini data were the only things really showing us here in the blue thing. And so from the sweet spot data release 1, which we're going to release hopefully by the end of this year, I used to say at the end of the summer, and it's still summer here, we will be able to cover this plane, and we'll be able to answer this question separate from survey. So I'm really looking forward to when that happens. Sadly, unfortunately, I'm good for her. Anya Wyant graduated, and that means I have to do this now. Because Kara is doing all the observations. We start in a couple of weeks, as well as doing the other work. So I hope that when I come back here, maybe again in a couple months or next year or something, I'll be able to present and answer what the color coding of those points should be, as I was teasing here with their residuals. But I think we have enough from the sweet spot sample of what is now 91 type 1a supernova observed in the first 4 semesters. But we'll probably only have about 70 of those in the data release. Just for mental sanity, I think we'll stop at the end of 2013B. It's always nice to just, these are all the data we're going to publish, because you're still always futzing with the latest ones. But we might advance. So we've had about 15 to 20 supernova in the good semesters, where we've gotten a good allocation of data of nights. We have another very good allocation this semester and next semester. I certainly expect that we will get up, maybe not to 144, but at least to 130 type 1a supernova. When I say sweet spot is observed, again, I've mentioned both their names, but since they did all the work in staying up, Anya and Kara have both worked really well. The remote observing net wind has worked really well. The observers and schedulers and equipment people have all been very helpful. I think that's been great. If you want to follow along at home, this is all publicly available. We just keep our observations and our target list publicly available because that was easier for us, and it's not proprietary. We, in fact, would like other people to observe them and coordinate some of those efforts. And in fact, what I found, much to dismay when trying to Google information about a particular supernova, our page now is one of the first hits, which wasn't what I wanted to know about the supernova, how many times we observed it, but rather I wanted a finding chart or some other information about it. So we've now covered, this is not prediction, this is actual, this is our redshift distribution. So this double peak is not our intent. It's essentially that there are nearby surveys that can do this, and there are nearby surveys that can do that. That's what you're seeing. You're seeing 2 magnitude limited sets of different types of local surveys. That's what's giving us this redshift distribution. We do intentionally follow some of these near ones to try to get very, very late time colors. We haven't done anything with those data, but there's another richness here. And we've succeeded in getting enough observations on most of those supernovae. And some of those early circled red points just had one observation. We still got something reasonable, but we think that's a little silly. So we're hoping to get at least 3 points in each for all the things. And we've managed to succeed in doing that for most. We have J for most. K, the sky is really bright in K. So we've, practically speaking, even in really good seeing, only been able to do K-band observations for things of redshift 0.03 or less. So we haven't been able to bring K out there, but J was our big question, and having both J and H will work out well with having optical and other things. Here are pictures of all those galaxies. Here are what we think will be 74 supernovae in the 2013 B sample. If you're very good at counting, you'll realize there are only 71 stamps here. Some of the host galaxies were shy. But we do have that information, and we will be able to produce and test what is the dispersion actually of the type 1a supernova in the infrared. We'll be able to investigate further any correlations in the host galaxy properties. If it's there, there's probably something to tell me about the supernova. If it's not there, I don't know what's going on. Maybe there's something we don't understand about the color evolution of the optical. Either way, I think we'll learn a lot. And we've developed the framework to be able to deal with these systematics. As we learn more about the astrophysics, then we can do more about the cosmology with future experiments such as LSST. Thank you.
All right, thanks, Michael. Let me open it up for questions.
I got the naive question. So why is it that supernova brightness is correlated with host galaxy mass? Okay.
So here, I can spin some stories.
It's heavy galaxy makes heavier stars makes brighter stars?
No, the problem is it's worse than that. It's not the case that the supernova. Okay. It is the case that bluer galaxies make inherently observed bluer, brighter, wider supernova. So that's the more direct progenitor channel question. Redder galaxies make fewer of those types of supernovae. But we know that there's some relationship between the width of the light curve and the color of the supernova and its intrinsic luminosity. So type 1a supernova, standardizable candles, we can take them from a factor of up to a few, but even throwing out 91 VG ones, 50% down to 15% by applying these corrections. After applying those corrections, we see this, in the optical at least, residual split associated with the host galaxy. So it's a little difficult to figure out. Do we have an error in our light curve fitters or distance inference that's based on having some particular sample of host galaxies that's this way or that way weighted versus what we actually have, to figure out which direction that means we've made a mistake. So that's why it's unfortunately a little tricky question to answer. But more directly to the point, I think there are two directions you would go. You would say there are various reasons to think that metallicity matters. Since, I mean, it's one of the obvious things, metallicity should always matter. You have more subtle things like the distribution of initial masses and binary systems, maybe it's a little different. But to be very specific, one thing I would worry about, although this is not specifically borne out by what we see, is if you have a short, so the other thing we see in the type 1a supernova rate is associated both with the total stellar mass of a galaxy, more stars, more supernova, like really that simple. But it's also associated with the star formation rate. And by star formation rate, I mean in the last few 100 million years. So people have talked about there's some delay time distribution of type 1a supernova. You can model that as a short channel and a long channel, or as one exponential channel. You sort of figure beyond the astronomer physicist joke going on here. But we don't quite really know exactly. And anyway, but I might be concerned that if it's 100 million years when you blew up, your local dust environment might be really contaminated from recent generations of core collapse supernova that have happened and do not look like our standard reprocess ISM. There's a story I could say. It might be the case that you have dust behind you. You're getting reflection from stuff. People like Li Fan Wang have written papers sort of talking about this. So these are some of the reasons that the dust you might see from supernova may not actually be exactly the same that you see through different lines of sight in the clouds. Anyway, I had one more thought, but I think I've been talking about it. Other questions? Yeah.
So, along those lines aside, right, why would one expect two things as opposed to a continuum of stuff? And, right, so you were talking about these two different,
Sure.
right? And so it seems a little, why two, right?
Right. So if you interpret that split as saying two different populations rather than a continuum, which I think the dust argument I agree with sort of talks about. Well, let me step back. You could argue that local dust formation, the dust gets reprocessed very quickly in some way such that there is effectively a cutoff applied. And that if you have some local dust, it's always some significant bit, and that would be a shift. I'm just making things up, but like that would be one argument. But I think many people do think, well, you have two populations. And they naturally would think about things like, oh, well, maybe this is the difference between having a single degenerate case, where you have one white dwarf accumulating material from a main sequence or red giant, although some of the most recent Type 1As have not allowed for 2011 FE or others, a red giant companion, that reaches a critical mass and then explodes. It's a single degenerate. And the double degenerate, my wife makes so much fun of me for studying transient degenerate objects. The double degenerate scenario of two white dwarfs merging. Now, people don't like the double degenerate because why on earth is it standard? Do they somehow reach some critical mass at the same time, or is the nature of explosion pretty much the same? And, but on the other hand, that explains why you got rid of all that hydrogen, which is a characteristic of things. It's a little harder to explain why you see almost no hydrogen in any Type 1A supernova in the single degenerate. But what really would bother you is, why should they be anything close to each other? Really, 10% different? Right, they're not even 10%. There's more than 10% variation within the class. Why should two different channels have that? Even if you want to argue that some accretion merging event reaches some critical threshold, it's very difficult to imagine those would be about the same. But having said all that, you could say, oh, these two populations are these different channels. These different channels probably have some different delay time distributions. Maybe that's the answer. I don't know. 10% is really hard to explain. Factors of 2 are easier. I should say, and I didn't put slides about this, and I actually sort of, are we still recording? Okay.
We could, yeah. We can cut it out.
Well, anyway, this isn't secret, but the Sloan 4 has a MANGA survey. So MANGA stands for mapping of nearby galaxies at Apache Point, or something like that. Anyway, it's to take a bundle of fibers. So Sloan has 649,000 fibers in its main spectrograph, and this MANGA has taken them, and put them into fiber bundles and made IFUs of them. And it's doing that to study nearby galaxies. It's going to study 10,000 nearby galaxies out to a redshift of 0.1 to try to get a resolved census of all these galaxies. So I really want to know what the host galaxies of all the supernovae we found look like, both individually, but almost more importantly, in the context of this survey that will set the next standard for understanding galaxies. We put in a request for an ancillary program to ambitiously study 500 of these galaxies, to learn things about what is the resolved distribution of things. Now, so the supernova factor has better resolution for their IFU than we will have, about doing things like the local H-alpha or things like that. But in that very same spirit, we'd like to know these things. And it's not important that the supernova be live, right? We're asking questions about the environment. So we're hoping that that might help tell us these things. And one of the things that it'll probably do pretty well is do the delay time distribution. Colleagues Orgarar and Danny Miles are interested in this. There are also people interested in core collapse supernova, which actually this will probably be even better for, because that's really the environment still there. Mario Mojas, Carlos Padenes are working and interested in that. But I'm hoping that will tell us a lot, actually, perhaps as well, about the different environments that the Type 1A supernova come from, and what those environments look like in the context of their overall host galaxy, right? Like I presented a very simplistic picture of galaxies. They have a color and a luminosity. They are much more interesting, complex things from that, with different merger histories, different star age distributions, different star formation things, and maybe there are properties like that that will more clearly reveal to us what the differences in the progenitors or the environments of the Type 1As might be. we're still waiting to hear as to whether or not that got approved. That was the only non-public part. But
do we have questions by people who are listening remotely?
They're muted right now. We got Robert, Jelko, and I'm assuming Chuck Clayton. The audio is on this thing, so.
All right. Well, if we're out of questions, let's thank Michael again